David there.
All right, so let's start out with any questions on chapter 6. Before I eventually did post the lecture. You were asking when they'd be posted, and sorry it took so long to get it done, but it is.
I haven't even watched it online. So
Say it again?
I haven't even watched it yet, so.
Okay. Well, it is as exciting, no doubt, as you remember. All right, so chapter 6. You about that question?
Question 73.
Car driving around a flat circular curved road with a radius of 500 meters. All right, so draw the picture. So this is 6.73. And let's pretend we can actually have a marker that can show up. Now let's do a back view. That's supposed to be a car. Radius curvature was 500 meters. So the car at this point right here, going that way. So we have massive car, which I suspect is irrelevant. And we have the static coefficient is 0.3, is awfully low. Use the work example, and the pages are off if my note is correct. Maximum speed can go without slipping. All right, so what's step number 1?
Force diagram.
Car. So what are the forces acting on it?
Static friction.
Assuming that this is the inside of the curve this way, to center. All right. Next step
Acceleration.
is in which direction?
Into the page.
Sorry. Into the page? Or in?
It's headed, since we're looking at it from a back view, right?
Correct.
So would it be into the page?
It would not.
No.
See in the same direction as the
Oh.
static friction, right?
Yes, yeah, the acceleration is going to be in that direction. So the whole idea of centripetal motion is the fact that the acceleration is towards the center of the circle. By the way, this is not part of the force diagram. Just as a note, not part of the force diagram. All right, so we've got the direction of acceleration. So what coordinate system do you want to set up?
J hat going that way, and hat going that way.
All right. I hat and J hat. And now what?
Equations, because there's nothing to decompose.
All right. So we have our I hat equation. Now, I hat is not equal to what I'm about to write. This is just a note off to the side to indicate which equation it is, just to keep it track in my head. So Fs is equal to M A sub C. And then my J hat equation, Y minus W equals 0. And now, substitution. What do we have independent equations for?
Centripetal acceleration.
And
normal force and weight.
weight. Not an independent equation for normal force, that's always problems dependent. And one more.
Friction.
Yep. So we have, since we're at an extreme, we're trying to find the maximum speed. the car can go without slipping, and so we are at the boundary of static friction. V squared over R, and then Y equals mg. And so now it's a matter of plugging into there. So mu s mg equals mv squared over R. The masses cancel, and v becomes the square root of mu s gr, which is something. I figured you could do that. So 0.3 times, let's just for the sake of it, assume we're on Earth doing this problem. Times 500. All right. I feel like your question was something else other than what we just did.
No, well, on the homework thing, you just showed that equation at the end, so I didn't know how you got to that point.
Ah,
So
okay.
Now I see that.
Okay.
You explained it.
Now, the mass did cancel out as I expected, because they usually do, but actually we do need the mass for part B, just since we're here. They asked for what is the force. Well, this is our centripetal force here. Again, centripetal force is not some new force we throw into the diagram. Centripetal force is not, we're not drawing a separate arrow for centripetal force. So once we have the V, you plug in, find the acceleration. Well, actually several ways of doing it. You plug in for V, plug in for R, plug in for M, and find the force that way. Or since the centripetal force is the static friction, you could just do US mg. Right. Any other questions about this absolutely spectacular problem?
I think 74 is related to it,
Yeah.
but for C, I think I'm just confused with the friction part.
So, sorry, back up. You're confused with this?
No, for 74C, when it's bent,
74B.
74C,
C.
yeah.
It's like a misspelling. Let's see. Would including friction in the problem increase the maximum speed allowed or decrease it? So they give us the angle there. And so presumably, let's make sure. Maximum speed can go without slipping. So we find some optimum angle here. Oh no, we're given the angle, we find the optimum speed. B, centripetal force, similar to what we did. That speed that we would find for part A is that if it were completely frictionless, at what speed would you take this curve so that you would just stay in that same level the entire time? If you went slightly faster than that, you would slowly slip to the top. If you went slightly slower, you would slip down to the bottom. So it's that optimum speed. So if you added friction, increase the maximum speed allowed or decrease it, well, in some sense, both. You could then drive faster. Let's see, maximum speed. Oh no, it would not be both. It would increase the maximum speed. Because you now have an additional force. Because you have normal force this way, weight acting down. If it were frictionless, friction, you can increase the speed because you now have an additional force acting in this direction. So there's a component of friction
So
that
friction
adds to the
acts in
centripetal.
This friction acts in this direction?
Friction has to be parallel to the surface. So friction, if you're driving above that optimum speed, then friction's acting down the ramp.
Oh, okay.
If you act below the optimum speed, friction will be acting up the ramp.
Wait, can you repeat that again? Friction, if you're driving below what you said before?
if you drive, all right, so at optimum speed, you're gonna stay at that same level on the bank curve. You drive faster than that, you're gonna slowly drift off to the top of the curve, to the top of the bank. So therefore, if you're driving faster than that optimum speed, your tendency is to be moving up the ramp, and so friction is acting down the ramp on the car, I should specify. If you drive slower than the optimum speed, your one tendency is to move towards the bottom of the ramp, and so friction is acting up the ramp.
And it's always pointed towards the center, right?
The acceleration, the net force is towards the center. So in this case right here, wow, apparently I was disoriented there. We have weight acting down, we have normal force acting this way. So without friction, if I actually added the two forces together, normal force this way, weight acts down like that. The net force is in that direction. You throw friction into it. And so then you have, let's say you're going over the optimum speed, so friction is acting down like that. You have normal force, friction, and then weight. So that would be the net force. Did I answer your questions? Right. Other questions on this problem?
I do have a question for chapter 7.
Right. Any other questions on chapter 6? Does anyone want to deny Precious her understanding of a problem in chapter 7? They got your back. All right, so chapter 7.
I think I didn't understand the textbook explanation for 45B.
All right, so Clay Anderson experiencing weightlessness, there should be in quotation marks, on board of the International Space Station. Why would astronauts in orbit experience weightlessness even if they experience a gravitational field and therefore gravitational force? So, planet called Earth, satellite, or whatever it happens to be orbiting. From a conceptual point of view, let's actually go back to sort of a Newtonian thought experiment. So I have a mountain right here and I put a cannon on top of it. If I shoot the cannonball, what's it going to do?
Roll back.
Roll back.
Wait, is the,
What's the cannonball going to do?
was the cannonball, oh, it's
Yeah, and more specifically, Max, you did the hand gesture.
like that?
Yeah, it's, so Newton then started thinking about it. He said, well, suppose I shoot it faster. Well, if I shoot it faster, it's going to go farther. And then faster it'll go farther, and faster it'll go farther. At some point, the arc that the cannonball experiences, and we're of course ignoring air resistance, at some point that arc right there is going to match the curvature of the Earth. So if this thing is shot so that it can actually travel all the way around, that's called an orbit. In essence, once I shoot it in this situation right here, the cannonball starts to fall. Well, it's still falling over here, just that it keeps missing the ground, which I think was the Phantom Toll Booth, where someone learned to fly by throwing themselves over the ground and missing. In essence, that's what's going on here. So something in orbit is actually just constantly falling. It just keeps missing because that curve happens to match the curvature of the Earth. So in this particular case of the feeling of weightlessness, of an apparent weightlessness, is the fact that the space capsule, or the shuttle, whatever they're in, space station, and the astronaut are both orbiting, so in other words, they're both falling. Because they are both falling, they're not experiencing any normal force, which is generally, because remember, if you stand on a scale, scales measures normal force, flashback a couple weeks ago. And so since there's no normal force there, that it seems like there's no weight. Is that sufficient?
So it's in free fall, because that's what the textbook says.
Yeah.
Okay.
I mean, free fall means that the only force acting on it is the force due to gravity. It just has so much sideways velocity that it, yeah, as I said before, it just misses the Earth. Any other questions from 6 or 7? Enrique?
Yeah, can you go over 41 on 7?
The 3 billiard balls?
Yeah.
So this is 741. Let's see.
Sorry.
Can't believe you're showing me noise in the middle of class. Shock. M1, M2, M3, and oh, that's the wrong drawing. So the 2, the 8, and the 4, those are just the number of balls. This is 2 meters. That's 1 meter. And mass of each of them is 0.15 kilograms. And lost it. Given the coordinate system shown that the mass, determine the gravitational field at x is 2, y is 0. So right here, the gravitational field. I didn't, actually, I'm trying to remember if I mentioned gravitational field in class. I know I did a video on it that's posted, but I don't know if I mentioned it, talked about it in class. So, did I talk about gravitational field in class?
I don't think so, but it was on the book.
Okay. That, just a quick background on the whole idea of fields. It's, how does one object know another object exists? If I have 2 masses, they're attracted to each other, but how does one know that the other mass is there? And so one of the things the theorists came up with, or the early theorists, was this idea of a field, that an object gives off something, a field, which the other one senses. So one mass doesn't know the other mass exists. One mass knows that there's a gravitational field passing by it, and then goes trying to find the source. Slightly more complicated when we get to electricity, but the same basic concept. So, if the field is something that's given off by one mass, without the, doesn't need the other mass for the field to exist. The field just exists because of one mass. So, if I have a mass here, it's giving off something, whether I put another mass into the system or not. And so if I think about that, the gravitational force, the magnitude, big G, mass 1, mass 2 over R squared, well, the field should be related to the force, but it can only have one mass in it, so basically, that's it right there. So, what they're asking is, and is the gravitational field at this point because of each of these. And so this gives off a gravitational field. And now, I hate minus signs. I'm forgetting if there's a minus sign. Yeah, there is a minus sign there. So the negative G mass over R squared, R hat. So this creates a magnetic, or wrong class, a gravitational field, negative R hat direction, which means it's towards the center. This one's gonna have one in that direction, this one's gonna have one in that direction. So once you do a plug and chug, you'll end up with three vectors that you need to add together. So the gravitational field from mass 8, negative, we'll just stick the number in here, times 0.15, divided by that distance there, which is 2 squared, pointing towards ball number 8. And then gravitational field for mass of, say, the number 4 ball, negative G times 0.15 over 1 squared, R1 half, or R4 half. And then the last one, G of 2, negative big G times 0.15, which is the mass creating the field, over
Square root of 5.
squared. So now it's a matter of vector addition. It's now become a math problem. Depends on how you want to do this. Let's just set up a coordinate system. I hat, J hat.
Those vectors you use in, it's not I have and J have, no? No, in there.
Those are the radial unit vectors. That's R hat.
R what?
R hat.
R hat.
The radial unit vector, I hat, J hat are always dependent upon, or in the direction that we have to define. I'm saying, so right there, I'm saying I hat's that way, J hat's that way. I could have made I hat in that direction and J hat in that direction.
Okay.
It's dependent upon how I want to define it in the system.
And then they have different number for each one, no?
Yeah, so R hat is a unit vector
for
that's
two,
pointing
for-
away from the
okay.
center. So I have subscript 8, subscript 4, and subscript 2 here.
Okay.
So they each have a different reference system.
Okay.
Alright. So what I'm trying to add them, I need to get them into the same coordinate system, so this is why I established an I hat, J hat here. This numerator is the same every single time, so I'm just gonna let that be the letter Q. Why not? Use your calculator to find the actual value. So, G8 is pointing in that direction. It's my Q divided by 4. So negative Q over 4 I hat, because it's pointing that way. G4 is pointing up. So it's negative Q over 1 J hat. Positive, because it's going up. And then the last one, it's going to the left and up. So we need to break that one up into triangles here. So I've got this, I know that's 1 and 2, and that is square root of 5. So my magnitude is Q over 5 times.
It's 27 degrees.
We actually don't need to know the angle. If you do, that's fine, there's nothing wrong with it. It might introduce some rounding into the problem. But I know that the component in that direction, the cosine of that angle, is 2 over the square root of 5, negative I hat, plus 1 over square root of 5 j hat. Now we have a rectangular form. Add up the i's, add up the j's. I forgot to ask 741, or is there a desire from anyone to actually finish the problem, or is this sufficient? I will stop it there then. As a side note, we add it all together, we end up with the gravitational field. If I then threw in a question of, I now stick a 1 kilogram mass sitting right at that spot, what is the force on it? Well, at that point, I would just take that mass and multiply times the total gravitational field. Other questions from 6 or 7?
So gravitational field is gm r squared. I thought it was gm, it's just r. Does the r have to be squared?
R should be squared. Yeah, because all you're doing is just taking the force and dividing by mass. All right. Step next door, grab the quiz.
Question he's gonna give us?
It's not meant for spine, but the camera was left on while I was gone.